Hey everybody, welcome to CS302 Assignment 3, and we're going to be implementing a family tree. I guess similar to the one, on the left and right picture. The left picture is a much more pleasant family tree, whereas the picture on the right is more the computer science version of a family tree, which is not really as pleasant. So I guess the idea in this assignment is we'll use a binary tree to represent our family tree. So each element, each person will have at most two children. And essentially what's going to happen is everybody has a value, which will be a wealth. So you can see here in the tree on the right side, the root has a wealth value of 4, and then we have wealth of 5 and 6 and so forth. So what we're going to do is we're going to say that the grandparents, I guess this will be an inheritance, but I guess maybe in this version it'll be a different version of inheritance, as the grandparent is going to swap the wealths of the grandchildren. So that's how the inheritance is going to be distributed or redistributed among the children. So this program basically is going to do this. So for every first cousins, we're going to swap the wealth value. So for example, in this tree, the root has no cousins, so we don't update the root's value. This element has no cousin. Now, the 5 and 6 are siblings, but they have no cousins. But at this level right here, these two nodes are siblings, and then 10 and 11, these are also siblings, but among them, these two elements, these pairs, these are cousins. So 10 and 11, those are 7 and 8's cousins and vice versa. So this assignment means what we're going to do is take the sum of the siblings. So here we have the sum of 15. And the sum here is going to be 21. And we're going to swap them. So we're going to assign 21, 21, 15, 15. So we do this at every level of the tree. So for every first cousins, we're going to actually apply this technique. Now, of course, you could have certain cases where you have no cousins, or we're not going to be able to do this. But we're going to essentially using, I guess, the grandparents' inheritance, which is going to be a very strange inheritance rule. But we're going to just have it where we redistribute, we swap the wealths among the cousins, among the first cousins of our tree. So that is the idea for this assignment. So let's go ahead and now discuss the actual details for our binary tree class to allow us to implement this algorithm. Okay, so we're going to have this family tree class, which I guess makes sense because it's going to be a binary tree, but more specifically, it'll be a family tree of some sort. So we're going to have several members of this class. So first we have our bin tree node class, or sorry, a bin tree node struct. Remember, this could be a class, but I chose a struct instead because I guess the convention, at least my convention, is that for simple data types or simple custom types, we use structs, or I use structs, and for more complex, I use a class. So it's just my own personal convention. So of course, this could be a class, bin tree node, and just have everything be public would have been the same thing, but either way, it's fine. So each node of our family tree will be a bin tree node. So we have an int wealth, which these blue numbers here represent the wealth. Then we have a left and right pointer. So left and right child pointers. So pretty much very much on pace with a binary tree. Then we have our two constructors for our bin tree node. So it just, again, as we insert elements into our tree, it's always good to make sure that we will, when we create a new bin tree node object, we always set the left and right pointers to null. So this first default constructor sets the wealth to 0, the left and right pointers to null pointer, and then the actual constructor body will be empty. And this other constructor, this parameterized constructor, we pass in a wealth value, we assign that to our wealth field, and then we again set our left and right to be null pointer, just to ensure as we insert elements into our tree, let's say at the very end when we insert our final elements, which might be leaf nodes, you might forget to set the left and right to null. So these constructors will ensure that that will never happen, so you don't end up having this mistake in your program by accident. So that's going to be our bin tree node. Every element of our binary tree or our family tree will be of type bin tree node. Then we have our bin tree node star root. So that's going to be our root pointer for our binary tree. And then we have a set of functions. So let's go over to public members first. So we have our binary tree or our family tree constructor. So our default constructor, we'll just set the root to null pointers. That's going to be given to you. So I have it documented in the PDF, but you can just, we already have this. So we set the root to null. Now, our second constructor, we pass in a vector. This constructor is going to build a binary tree from an array. So you're going to actually call the build tree function within this constructor, and its build tree function is going to be recursive. So this function is private, which will be called in this public member function or this constructor. So these public members, for the most part, are going to be wrapper functions, and internally we're going to write these recursive functions I'll get called. But I will go over the build tree function later in this video. But this video, essentially, we're going to be taking an array, and this array is going to represent a binary tree, and then we're going to construct this kind of tree-ish structure from the array. Then we have the destructor, which of course will deallocate the entire tree. This function calls deallocate tree. And this function is going to just be a simple postfix traversal that deallocates the entire tree. It's actually going to be the same exact code as post order. So you first call deallocate tree left, deallocate tree right, and then you delete the pointer R. So it's pretty simple, just a simple postfix operation. An output tree function, again, is this public function right here is called in main, and this function internally is going to call output tree, this overloaded one. We're going to pass the root pointer into this function, so this will be able to recursively traverse down your tree. So the output tree function is going to just be a prefixed output of your binary tree. Then the last function we have is update inheritance, which is again a wrapper. So we're going to call this in main, but internally we're going to call the overloaded update inheritance. We're going to pass in the root, and this function will traverse down the tree using a pre or post order traversal to update the cousin's wealth. So really not much to say about the overall class structure. I think the actual functions speak for themselves. Let's go ahead and now talk about how do we actually, given a vector of integers, how do we construct a binary tree out of it? Let's get into that part next. Okay, so for the other constructor, the one that we explained a second ago, which is this constructor, we pass in a vector, and we want to construct a tree out of this vector. So in main, I wrote the main for you. You're going to read from the file, or actually the code provided to you in main is going to read from a file, which will consist of just a set of numbers, and you want to create a binary tree of these numbers. So suppose your input file that's given to you is going to be 4, 3, 2, -1, -1, 8, 3, just given to you like that. And of course, the vector is now going to be populated with these numbers. So these elements are given to you kind of in this level order. So this element will be your root. These are going to be the next level, and this is going to be your next level. So we can see it like this. So it will look like this, the binary tree. We have 4, then we have 3, 2. Now, these -1s in the middle represent null pointers. So you have a null pointer here. So you can see that we have a null pointer, which I can just sort of erase that. And then we have 8 and 3. So -1s denote null pointers, and we're going to use that in the middle. So if we have any gaps in our tree, so if we have, like in this case right here, 3 would have no children, we put -1s in this input file or in this vector to denote that that's a gap in our tree. So we're going to pass in this value, or sorry, this vector into the constructor. And then we're going to, in our constructor body, we're going to just call build tree, pass in this vector, and we're going to pass in the value 0. So this parameter, standard size t is just really a large unsigned integer. So typically for array indices, you want to use size t instead of int because size t can store large values. And if you're using an indexing value or a size of a structure, size t is a better data type to use than int. Although int would be okay as well, but I guess it's still a better habit to use size t to represent sizes of vectors. Even for the string type, when you call the length function, it returns a size t value, not integer. So sometimes on your compiler, you could get a warning when trying to assign a size t, which is an unsigned int, into a signed int. So again, not a big issue, but just FYI. So let's go ahead and discuss how would our recursive function build tree take this vector and create this out of it. Let's go ahead and get to it. Okay, so this constructor, as given to you here in this PDF, it'll contain just one line of code. Root equals build tree, and we're passing in the family members vector, and we're passing an index of 0. So we first call the function build tree, and pass in the vector, and you pass in the value 0. Let me go ahead and just write this out over here. Build tree. I'm going to just pass in just 0. So we're going to pass in a vector as well, but I want to focus on the value 0 for right now. So 0 is going to be our index. So in this function body, we're looking at this element. So we return a null in this function. We're returning pointers actually up this tree, and then the parent will catch the child. So actually, this is sort of how AVL trees build themselves. So when we go into AVL trees, will make more sense, but this is how AVL trees work. So we're going to create this we call this function right here. So in the function body internally, we can create a local variable r, and we're going to allocate a node to this pointer. And we're going to assign the value of 4 because that's the value at index 0 of this array. So we have to now construct the left side and the right side of this node. So we're going to now just do this. I'll give this away to help you. We're going to do this, and we're going to literally in our code do this. So r left equals build tree. And I want to pass in the index of the potential left child of 4. So from our original picture, this element right here is our left child. And I actually gave it a formula here in a PDF. So for any index multiplied by 2 plus 1 is the index of your left child. And any index plus 1, that quantity multiplied by 2, will be the index of the right child of this array. So as you can see here, 4 has 2 children, 3 and 2. 3 has 2 children, -1, -1, which means null and null. And 2's left child will be 8, and 2's right child will be 3. And then 8 and 3 have no children because these go beyond the bounds. So 8's potential child would be at index 11. And it's 2 is beyond the bounds, so these two elements have no children. They're both leaves. So we're going to go ahead and pass in the index of 1 into this new function call. So what happens now, I'm just going to erase this temporarily so I don't get too much cluttering in my code, or my drawing here, sorry. We're going to call build tree, and we're going to pass in the vector and pass in the value of 1. So index 1 is not outside the bounds of the vector, and it's not -1. So internally, we're going to create an object. and assign the value 3 into this object. So now we have to set 3's left and right children. So right here, we'd have to call, well, we have to first say R left equals build tree. And the left child of index 1 would be actually 3. And in this case, when we call the function build tree, pass in the vector and pass in the index of 3, well, we have the value of -1, which implies that this is going to be a gap in our tree. So we're going to return a null pointer. So what happens is when we call build tree, build tree 3, it's going to return a null pointer. Okay, cool. So it returns null. But what happens to that null? Well, the function call above, when I wrote this out a second ago, I had this written. I'll rewrite this again. So we wrote this. R arrow left equals build tree. We passed in the vector, we passed in the value to index 3. So this function returned a value of null pointer. So this node's left pointer will be assigned to whatever this function returned, and it returned a null. So we're going to assign a null to this left side. So now, after we do that, the next line of code is going to be, well, I'm going to say R arrow right equals build tree, pass in the vector. I want to pass in 3's right child index. So right here is index 1 is where 3 is. So 1 plus 1 and 2 multiplied by 2 will be 4. So index 4 is going to be where 3's right child should be. I pass in index 4. In the function body, we hit a base case because index 4 has a value -1. So we're going to return, this function is going to hit the base case, and it's going to return a null pointer. So R arrow right is going to catch that null pointer. So then the result is going to be a null is assigned to this. And now at this level, when I call build tree 1, I actually set R's left and R's right child. So now I want to return R. So I'm going to return the address of this node up to tree. And what happens actually? Well, if you recall a second ago or earlier, we did this. So at this level where we had the local variable R pointing over here, we had R left equals build tree 1. This function returns the address of node 3. So this node right here, this node's left is going to be assigned the result of build tree 1. Well, build tree 1 returns the address of the node 3. So what's going to happen here is it gets tossed up the tree, and the potential parent, which is at node 4, its left side will be assigned to the address returned by build tree 1, which will link that up. So 4's left child is not going to be 3. And now we have to call build tree next at this level where we're at this function call right here. We have to call, R arrow right equals build tree. I'm going to pass in the value 2. So what happens now in this function body, 2 is our index, and 2 refers to this element right here, and that's not -1 or beyond the bounds. So we're not going to return a null. We're going to, in this function body, we're going to declare this R pointer, and we're going to allocate a node to this with the value of 2. And then what's going to happen, just to sort of, speed this up, what will happen is we're going to call more recursive functions. And what's going to happen is we're going to we're going to go ahead and call build tree again. And we're going to create another node with the value of 8. Then we're going to call the function 2 more times. But when we're at index 5, we're at this position where if you take 5 multiplied by 2, it goes beyond the bounds of the vector, which means that index 5 has no children. So we're going to set a null pointer, and null pointer. Then we're going to go ahead and return the address of the node 8, and the parent above r's left will be assigned that return. So it's going to catch that node. Then we're going to go ahead and call r arrow right, call build tree, and pass in 6, which internally is going to, we're going to simply just declare a pointer r and assign a node to it and assign the value 3. Then we're going to call build tree. We're going to do r arrow left build tree and then r arrow right build tree. But in this case, since our index is 6, the left and right indices will be beyond the bounds of our vector. So in both cases, a null gets returned. And then r left will catch it. And then r right will catch it. Then we're going to return r up the tree. And then the node 2, its r arrow right will be assigned to build tree. And I passed in the value of 6. And then r arrow right will be assigned to that, which means it's going to catch what that returns. And now at this level, where r points to this node in this function call, we set r's left, we set r's right, we then return r, or the address of that node 2, and then the node where r equals 4 was waiting on this line where we had r arrow right equals build tree, and we pass an index 2. It's going to get assigned to what the build tree function returns. So it's going to link this up. And now at this level, where r points to node 4, it assigned the left and the right. It's going to return r up the tree and return back to the constructor where the root equals build tree. So the root is going to catch that node, and then we have our tree built. So we simply, at each level, we create a node, and then we set the left and right equal to the recursive call build tree, but we pass in the potential left and right indices in. It returns a pointer back, and then the r left or r right will catch that result. And then that's how we sort of link the nodes up the tree. So that's going to be how build tree works. Let's go ahead and discuss the update inheritance function. Okay, so for update inheritance, suppose we had the following tree given to us like this. So the public member function would get called in main, and internally in the function body, there only will be one line of code. Just call the private function update inheritance and pass in the root, and then you would recursively traverse this structure. So update inheritance, let's see, where is that? Here it is, right below actually. We're going to, of course, update our tree. So I'm going to go ahead and write the value r. Now, of course, I use the name grandparent to help us understand what this r represents. So we're going to have a grandparent passed in. So we have to find the grandparent's grandchildren. Well, I guess there's no real shortcut to this. I mean, here's the first grandchild right there. Since we have a null, this would be the right grandchild, but it's a null. Then we have this grandchild, and we have this grandchild. So we have our grandchildren right there. And there's no real shortcut. So it's r left left, r left right, and so forth. So we have to determine if we even have any grandchildren. If we do, okay, well, we have to add up the grandchildren. So these grandchildren right here have the value of 10 plus 0. And here we have 3 plus 9, so 12. So we have to, of course, swap. So you put 12 over here, 10, and 10. And after we do that, well, we have to now recursively call update tree on the left and then on the right. So then we go to the left side first. This will be your grandparent at this level. So where are our grandchildren? Well, we have these two elements as the grandchildren, 6 and 8. But we can see on the right side, there are no grandchildren. So 6 and 8 have no cousins. So then we just automatically just go to the left. And same idea, this is basically going to be just a pre-order, but you have to do a lot of checks to make sure, how many grandchildren you have. If, let's say, the grandchildren are actually, if they are in fact cousins of each other. If they are updated, if there's no cousins, then we traverse. So really, we just simply, for every level, we have to just find our grandchildren, determine if they are cousins of each other. If they are, we sum and then swap values around, and then we go to the left side and then the right side. So it's not much else to say other than that. So hopefully you see what you have to do. Really just a few extra checks, but it's just going to be really pre-order traversal of this binary tree. So let's go ahead and summarize up the rest of this assignment. So the output tree function shouldn't be hard to write. It's just a straightforward pre-order traversal of your binary tree. And the allocate tree is rather simple as well. So here's the main that's going to be provided for you. So we're going to read in the file through a command line argument. And this while loop right here is going to simply read in every element from the file and push it to the back of the vector. I create a pointer called old country, a family tree type. I allocate the object right here. I output the original tree, and I call the output tree function. Then I call update inheritance. Then I output the tree once again after the inheritance. So on CodeGrade, it will match the results of output tree beginning and the end. I used a pointer for this because, I don't know, I think it looked cool to draw the arrow symbols instead. It made it look cooler. So then saying at the end delete, I guess it makes the code look more Java or C# like. But anyway, that's the main provided. So the input files you're given, let me go ahead and actually just give that to you. I'm going to take it so you can look at these. So I'm going to go ahead and just open them up right here. Let's go with this one first. Rather simple, perfectly balanced binary tree. We have a larger one, negative ones in the middle, contain some gaps. Rather not so hard to draw up. This one looks really bad, but it's really a lot. It's actually a very skinny. It's actually going to be almost a linked list looking binary tree. But here's the problem. This is a very huge, like a 500 node tree and a 500 plus node tree. So the original input, I was able to draw it out and verify my work and make sure my code worked correctly. On these two, I generated, I generated these numbers randomly to create big trees to have a bigger example. So I couldn't really verify this by hand, but I'm going to have to just believe that my program works correctly. I mean, if it works in the small cases, it should just correctly scale up to the big cases. So I'm going to just believe that it does work, which of course I might regret this later on, but that's okay. So we're going to use these on CodeGrade. Now I do actually provide the output here in the PDF for the first few. So I just compile it, run it with the kind of arguments, and there's the original and updated tree. I give it for the first 4, but then for the last 2, it's too big of a file, so I just don't have that in the PDF. But I can, of course, link the output files. I can put them into the canvas, and of course, it will be available on CodeGrade as well. So I hope this video did help you out. So I guess happy coding, and until next time.